Alrighty, I might just get one more minute for a few more to trickle in. Alrighty, so I think we're going to get started here. Hi, everybody. Thank you for making the time today to join us for the first edition of the Data for Decision Making Offshore Wind Energy Areas in Geoscience Survey Results Workshop Series. For those that don't know me, my name is Claire Kleinknecht. I'm the Research and Engagement Officer at MRC, and I'll be the host for the session today and for the rest of the week. Marine Renewables Canada is excited to be partnering with an excellent team of research scientists from the Geological Survey of Canada within Natural Resources Canada for this workshop series, which will present geoscience survey results from all three wind energy areas that are being explored in the current call for bids process, which include Middlebank, French Bank, and Sydney Bight. Today we'll be focused on Middlebank. For those that might be new to our organization, MRC is the National Industry Association for Offshore Wind, Tidal, Wave, and River Current Energy. Our goal is to champion Canada's growing marine renewable energy sector through advocacy, education, and engagement. A key aspect of our education work are these webinars, and particularly a series called Ask an Expert, which explores Canadians' burning questions about offshore wind. And we're excited to be expanding our programming with the new Data for Decision Making series, which is designed to connect subject matter experts with those who need data to plan and participate in the growing marine renewable energy sector. Now, I'd like to take a moment to recognize and acknowledge the traditional territories and Indigenous peoples of the different lands that we are all on today. I'm hosting this webinar from Mi'kmaq, the unceded ancestral territory of the Mi'kmaq people. Given that we're coming together to talk about offshore wind, I give us all an opportunity to think about the impacts that renewable energy might have on Indigenous communities and how we can improve our own understanding of local Indigenous peoples and their cultures to ensure that marine renewable energy projects move forward inclusively and respectfully. Before turning it over to our guest speaker, a few quick housekeeping notes. We will be recording this webinar and uploading it following the workshop to our website and YouTube page, but we will be stopping the recording after the presentation to ensure that the discussion period can be really open and allow for that. Today's workshop will begin with a presentation, as I mentioned, followed by a long discussion period with a team of SMEs available to answer all of your questions. And really, the intention behind this series is to connect you with the foremost experts in the field. So I encourage you to ask any questions that come to mind. Now, I'd like to welcome our first guest speaker of the series, Pierre Arnaud Desage, a research scientist specialized in sedimentology and sedimentary processes with Atlantic Division of the Geological Survey of Canada. Pierre Arnaud is the lead scientist for sedimentology and marine core processing at GSC Atlantic and is actively involved in the development of valorization of the GSC legacy marine samples collection. Today, he's going to be providing an overview of what geoscience data exists, how it's collected, key findings, and ongoing research in the Middlebank WEA. So thanks, Pierre Arnaud, for joining us today, and please take it away.
Sorry. Thank you, Claire. Merci beaucoup. Today presentation will be in French, but sorry, in English. Oh, my bad. But feel free to at the end of the presentation ask any question in both of the official language of your choice. Sorry, I have some trouble with the presentation. Today we will, I will introduce you some preliminary geoscience data from Middlebank and the program of GSC. First of all, I will just a quick outline. I will introduce Geological Survey of Canada, and then introduce the GSC Marine Renewable Energy Geoscience program, and then I will present GSC data and sample that have been inquired on during the program, and especially on Middlebank. And then I will present some preliminary results from myself and my colleagues on Middlebank. So first of all, just a quick introduction about the Geological Survey of Canada. The Geological Survey of Canada is one of the oldest scientific organizations, maybe the oldest scientific organization in Canada. We are a very large organization with a large mandate. We are over 50,000 people from coast to coast to coast. We have 8 divisions, 8 offices, and we have more than 45 specialized laboratories. Sorry. In terms of marine geoscience, so we have 2 main locations. One is in Dartmouth at the Bedford Institute of Oceanography, and we have some colleagues in British Columbia at the Institute of Ocean Science. We are doing active research in the Arctic, in the Pacific, and the Atlantic Oceans. We have close collaboration with both government, department agency, and agencies. Like, for example, we have good collaboration with GFO. We have also good collaboration with the Coast Guard to do marine oceanographic survey. We are collaborating with universities and also stakeholders. So the goal of the marine geoscience is to programs are to disseminate across multiple national programs that are focused on susceptible development and public safety, offshore natural resources, and ocean governance. So the Marine Renewable Program is funded through two main fundings. So the first one is the Offshore Wind Pre-Development Program, which is a part of budget 2023. And in that program, we are the part for Atlantic Canada offshore wind marine data collection campaigns. And we are also receiving funding through the Energy Innovation Program. And we have also some kind of funding or leverage through the Marine Geoscience for Marine Spatial Planning Program, which is a part of the 2023 budget. All of this program are ongoing until 2028. So we are in early 2026. So all the work presented today, we are finishing our third years. So we are almost mid-program. So we have collected a good amount of data and still going at sea this year to continue data collection. And we are starting to disseminate those data and the first scientific results. Just a quick, very basic for people in the industry, of course, but a good reminder of what we are talking about when we are talking about offshore wind installation. So we are talking about, of course, the installation of the turbines, but it's not only about the turbines. There is also some cables, especially so between the turbines, and we have also all the cables, or the routing cable, that is an important part that linking the actual offshore wind farms and the on-land installation that are important to consider. As you can see on this, at the top of the multi-beam data, that you can see like a cable routing visible at the bottom, at the sea bottom. So what is important regarding those infrastructure? We need water depth information. We need seabed sediment information, of course. seabed and bedrock to know the seabed and the bedrock below the surface and the subsurface. We need to know some engineering characteristic, the mobility of the sediment, and of course some geohazard and geoconstraint, that is kind of the underwater landslide, the gas, the salt, and also the parameters of the sand that can be, let's say, geotechnical constraints for development of an installation of the turbine. And we have also the anthropogenic features that, for example, at the top right of this slide, you can see a shipwreck, and shipwreck is are present on the Scotian shelf, and that's something that you have to take into consideration when you install your wind turbine. So the GSC program is divided into GSC, some initiative led by some my colleagues at GSC Atlantic, so the 6 main initiatives are the bedrock, the sediment mobility, the geotechnical properties, the superficial geology, the quaternary sediment, and the geohazard and geoconstraint. So all the data that will be presented today should be part and will be part of a mid-program report that is currently in edition, and that should be released at the end of this month. So this will be available in the NRCan Science and Technology repository. And we will have some limited data that will be released on the geoportal geo.ca. There will be multi-beam backscatter, some sub-bottom profile data, and also some station information. So if we are now looking more about the GSC data and the sample that have been acquired since 2023. Most of the data and most of the things that have been done by GSCA are, let's say, stored online on the GSC expedition database. And so on this database, you have the cruise report, there's some station information, seismic data, position of seismic data that have been acquired. And this portal, on this portal, you have data since 2060s, the 1960s, sorry, that are available and open access. And you also have analytical result on this portal that include, for example, grain size analysis. All the samples that have been collected are stored in the GSC repository here in Dartmouth. So we have ambient and cold core storage. We also have sediment samples, bedrock samples, but there is also legacy archive data and also non-digitized metadata in the collection. So if we are now focusing on the data, like the active data collection that we have done since 2023. So far we have done 12 expeditions. So we have collected 100 of stations, like that's sediment samples, photo, moorings data. We have tens of thousands of kilometers of sub-bottom data, hundreds of thousands of hectares of new mapping, which is multi-beam and backscatter. And we also have done mooring and land deployment on all the banks, and which is include Middle Bank. Some notes about also the data available in our legacy collection. So we have currently doing QC, so quality control of those data, because So we have hundreds of thousands of legacy data, for example, for the grain side that are available in our collection. But those have been analyzed in the 60s, 70s for most of them, especially on the Scotian Shelf. And we have realized that maybe those data, compared to the analysis that have been done in the past, compared to the modern analysis, may not be as, let's say, complete or accurate that is done now. So we are currently looking at doing the QC of those data. So the question that we are asking ourselves is: does the coordinates are good? Do we have the metadata for those data? And we are realized, for example, for the same samples, same location, we have multiple entries when often like different grain size, for example, so different values. So we are trying to QC to see like, okay, can we find those samples? Can we redo analysis using modern techniques on those samples to offer a better quality of those data? In terms of core analysis that I'm regularly, and this is the case for this project, done on the on sediment core. So we are doing X-ray computed tomography. So it's the same as CT scan for a human, but we do that for sediment cores, and we can have a nice view of the laminography, like the stratigraphy inside the core. So we are doing also multi-sensor core loggers. For example, when we are on cruise with a big ship, kind of, we can bring our MSCL on board and do all those analyses on the whole core on board. And then when we are going back in the lab, we can split the core and redo those more analyses on the core. So those analyses, like the data that we can obtain is like photography, the bulk density, magnetic susceptibility, the P-wave velocity, a lot of information that are really important for analysis of the core in terms of sedimentology, but also in terms of geotechnical parameters. We are also measuring the shear vein measurements, values, the transverse and longitudinal acoustic velocity. We are also doing subsampling and grain size analysis on those core, and some analysis that we are not doing internally are XRD, so X-ray diffractometer to get the mineralogy of the samples, and we can also are doing XRF on samples to have like the elemental composition of the sediment. And finally, we are also sending some sample for C14 dating in order to have time scale for the sediment core. We are also doing analysis on the superficial data, which include grain size analysis. So for Middlebank, our goal is to do grain size analysis for the superficial data on 80% of the station. And we are doing grain size analysis on the 0.04 micrometer to 32 millimeter fraction. And to do that, we need two instruments. We have a laser counter for the finer fraction, and we have a cam sizer for the larger fraction. The grain size analyses are currently in progress, and some of the analyses are done, but we still need to do some QC on those data. And we have also done visual analysis of sample photo, particularly to do boulder identification. We are doing XRD and XRF, so to know the sediment meteorology and sediment elemental composition of the station. So the goal is to do around 65 for Middlebank, 65% of the sample, like the station acquired for XRD and XRF. And finally, we are doing visual analysis on drop cam photo This is used for habitat mapping, for example, but also for boulder identification. So boulders, when I mention boulders, boulders are all the, let's say, rocks or gravel that are over a certain size. So we are talking about from 30 centimeter to 2, 3, 4 meters. And those are kind of problematic. We'll discuss that after, but they are problematic for pile installation. So if we are now looking specifically for middle bank, the data and the preliminary result for each activities. So in terms of bathymetry data, we have acquired since 2023, so in 2 years, 3 years, 96% of the middle bank WEA area, and we have the same equivalent for the backscatter. So on this, on the left, you can see the multi-beam data, and on the right, you can see the backscatter data. So we still have small part of the eastern section, western section of middle bank to finish. In terms of data collection, we have collected over 200 Van Veen grabs. So Van Veen grabs are small grabs. So it's you can see the Van Veen grab on the top right illustration of the slide. We have also do 26 IKU. So IKU grabs too, but way bigger, and they allow us to get through sand and to have like the first, let's say, 20 centimeters of lithology. So this is an example on the left bottom of the of an IKU result, kind of. And you can see we can do tray, we can do push core in those grabs. So just to know the surface, but also like the subsurface. We have also done 27 drop camera transect on middle bank. And those transects, so when we are doing those transects, is that we have a camera that is towed by the ship, and the camera is close to the bottom, and every X amount of time, the camera is taking a picture of the bottom. So on this 27 transect, we have hundreds and hundreds of pictures of the seafloor. If we are now looking at the superficial geology activity, so this activity is mostly focused to doing superficial geology maps, and on the, let's say, the classic way, so manual way, but also we are trying to do semi-automated maps with the help of machine learning in order to improve the efficiency of doing maps of the superficial geology. So these maps, like the superficial geology interpretation, is based mostly on the multi-beam and backscatter that were graded at a 2-meter resolution, which you have the two topmost figures, like representing the multi-beam and the backscatter. But you also need some data, like to do the delimitation and interpretation of the map units. So you need seabed photography, you need sediment sample photo, field grain size description. Ultimately, you need laboratory grain size analysis, but as these data are not currently available, the grain size have been estimated using a visually description. So it's so you have a more broader view of your grain size. Like you can divide into categories like mud, sand, gravel, cobbles. For the semi-automated approach, the model is using filters, so to detect spatial patterns, and this filter need to be, let's say, trained. Like it's like every AI or machine learning model, you need to train your model, and to train the model in that case, it's the scientists are using subsection of data that have been manually mapped, and based on the subsection, you can do a bigger section with the AI model. In terms of results, so this is the map for Middlebank. So with the units that have been identified, so these units are going from diamict to postglacial marine mud. We can see that there is a good diversity on Middlebank, but the bank is mostly dominated by postglacial sand, coupled with gravels and pebbles, and you have some, especially in the northern part, some section of diamict, so a mix of sand, gravels, like very heterogeneous. If we let's just do a quick close-up on a part of the bank, and what is the approach to do this map. So here you have a backscatter dropped over the bathymetry, and so you can see two units. So especially the postglacial gravel lag and gravelly sand sheets. And also the postglacial mixed sand, and then you can see like the picture that have been used to interpret those units, and you can see that the composition in terms of sand, but you also see on the bottom right that for E and F, you can see that there is sand, but there is also gravels and even more coarser, almost close to boulders grain. If we have now another close-up, so we are focusing on diamict units. So with a picture A, B, C, D from these diamict units, and we can see that this unit is composed like this mix, heterogeneous mix of sand, of course, but also a lot of pebbles, cobbles, and up to boulders. You can see on the C panel, like you have this big boulder at the top, and also on the IKU, we have collected this large cobble slash boulders. And now you have the result from the semi-automated approach. So what you can see is that the results are good for the semi-automated approach so far with the data that was available. Still need some work. We can see like that the model is still interpreted some bathymetry and backscatter artifact as let's say real unit or real features, but its artifact, it's especially being seen in like when you can see at the black arrows, like you can see those band and those like stripe doesn't really exist. That is artifact from the bathymetry and the backscatter. And on an other note that you can see, like compared to I have shown previously, the model is not as good as let's say human eyes to for example map the diamict. For example, there is a less representativity of the diamict. Everything is under work, so it will be improved in the future. If you are now looking at the sediment mobility initiative, so it's mostly focused on bank scale model, looking at the geomorphology, so the seabed features. Also, like under the umbrella of sediment mobility, we have the benthic habitat. So this activity is fed by mooring and lander that have been deployed over the last 3 years on the bank, especially a mooring on the southern part of the bank. We have on the multi-beam data we have identified some let's say furrows or some linear depression, and we wanted to monitor what happened to those linear depression that are going from the bank to the channels around the bank. So a mooring have been installed there, and the mooring are used to estimate the current velocity and current direction, and also the turbidity in the water that can give you really interesting information to let's say feed numeric models and calibrate numeric models. And there is also like this is the small video that you can see on the top right. We have deployed a lander on the bank. This lander was deployed over various bed forms in the central north part of the bank. So the first thing is the Bedford type analysis, and this activity have mapped or let's say seen several major bedform types on the bank. So that's include like large-scale sand ridge that you can see on the top right panel. This is very large-scale bed forms, but also some smaller bed forms like we have sound waves. We have, like you can see on the right bottom panel, like mega ripples, ripple scarrow depression. There is a lot of scarrow depression that is really interesting on the bank that have been identified. We also have like some sand rebounds, or I've mentioned before, furrows that can be interpreted at sand rebounds or furrows that are oriented toward the bank edge. And all this, let's say, all this for all these bed features, seabed features, the orientation, the height, the wavelength, and the asymmetry have been obtained using the bathymetry and the backscatter. Then now with the model, so my colleague Mike Lee with a colleague at DFO are working to get high resolution wave model, but also high resolution currents model. Currently, the wave model have been completed in 2025 for middle bank and for this part of the Scotian shelf. The resolution of this model on the Scotian shelf, like at a regional scale, it's between 3 and 5 kilometers. But for the proposed WEI, as you can see on the bottom right panel, the resolution is way better or way finer, with resolution up to 50 to 100 meters. And currently, the current model is, let's say, under work and will be completed in 2026. So in part of this activity, there is also some work that have been done for benthic habitat identification by my colleague Vlad Kostilev. It's based on the 28 photo station transect, and just really brief result. But you can see my colleague have identified sand that is dominated by sand dollars on the top right of the picture. We also have horse mussel reef, sea cucumber on the seabed units that are dominated by gravel, and there is also very interesting features of shell ash that are located in very let's say, very limited pockmark shape, like depression shape. And in those depression shape features, you have all these shales, but also this benthic fauna, possibly tied to seeps. If we are now looking at the quaternary sediment, so the idea of this activity is to do like isopac maps, map tunnel valleys that we know that can be problematic for offshore wind. So it's based mostly on seismic data, so historical legacy seismic data that include sub-bottom profile, but also airgun, sparker, boomer data. But since 2023, we have been able to collect some UNTEC deep toe seismic data, but also sparker surface toe data. And you can see on the right panel, that is the legacy data. So we have not so much data on middle bank, but we have been very successful to acquire new data, especially sub-bottom data, especially parametric, using a parametric sonar, which give us a really good resolution and really good data compared to, let's say, classic sub-bottom, like for example, the Knudsen all-mounted sub-bottom profiler. So we have a good amount of those Knudsen data. We have less Kongsberg or the parametric sub-bottom data, but we are hoping to get more this year and maybe toe seismic too, towards seismic too. So how it is an example of the legacy data, so that it's the line over a part of middle bank from 1994, acquired using a sleeve gun source. So it's kind of it's a type of air gun, and so it's digitized line. So it's of course the resolution and the qualities could be better, like if you compare to modern data, but it's still a very good information. And my colleague Calvin Campbell and Ned King, especially Ned King, have been able to interpret or start the interpretation of those data. And what we can say is that if we are going from, let's say, top to bottom, so we have at the top we have a complex sand and gravel sheets that are up to 20 meters thick. And those are usually topped with sand ridge that have been identified by on the superficial geology. And then you have like multi-phase glaciogenic sheets that are very heterogeneous, that can go from to boulder range. Presence of boulders is not easy to let's say determine with the let's say the resolution of those data, and especially if the boulders are not as big as, for example, 4 meters, but smaller. And what is also really interesting that you can see you can see on the figure, I can show you, but you have some V-shape depression, and those are potential glacial tunnel valley that can go very deep, and so they are really characterized by a very chaotic signature. And we have, like, according to my colleague, that those tunnel valley are more present or more intensive in the northern half part of the middle bank. This work is still under progress, and hopefully with modern data we can my colleagues can increase the let's say, interpretation of the seismostratigraphy of Middlebank. We are now looking at geohazard and geoconstraint. So today I will just present the result from glauconite and boulders identification, but we are also working in this activity on banked processes and density flow, so that are potential geohazard when you are looking to install any type of infrastructure on a continental shelf. So in terms of boulders, like the problem with boulders is that if you have too much boulders or too big boulders, that seems logic, but you will have some difficulty to install, like let's say anything on the seafloor, like or under the seafloor. If you, for example, are doing pile installation, if you have like this massive 2 to 4 meters or even bigger rocks, like you can't really go through that, or you have to find a solution kind of that to go through that. So the better way is to map those boulders. So based on the over 200 grabs and 25, 26 camera transect that have been done, we have identified, so this is the red dot on the map, like 21 sites with boulders. Those boulders are never, so the boulder identified at the surface at least, never bigger than 1 meter. They are usually associated with so a heterogeneous mixture of sand, pebbles, and cobbles. And the next step is to trying to get the better resolution possible for the multi-beam in order to do like automated identification on those boulders, on either on the multi-beam data, so the bathymetry data, or the backscatter data. We are also looking at the glauconite. So why we are looking at the glauconite, for maybe people that are not in the industry, the glauconite is a iron-rich phyllosilicate, and the problem with this phyllosilicate is that when you are trying to when you applied a stress, so let's say you are trying to add a pile on the seafloor, this stress will modify the structure of this phyllosilicate, and then it will kind of becoming really hard, and so you have a lot of difficulty to put infrastructure on seabed that are let's say fair amount of glauconite. And that have led like to some problems, especially in the east coast of the US, and also in Belgium and in England when they wanted to install monopile, but they don't like they found some high amount of glauconite in the sediment. On the Middlebank, so we have used XRD, so mineralogy identification, to try to locate and identify glauconite. And on Middlebank, on the WEA, the glauconite is mostly, and it's not surprising, in the deeper channel. We have concentration of between 1 and 6% of the mineral assemblage that is composed of glauconite. We have only found one sample on Middlebank, like on the bank, that contain glauconite. And what we, it's not really surprising because so shallow water are not very suitable to the glauconitization process, so the process to form the glauconite. But there is always the question that is this glauconite coming from like the place or coming from somewhere else, or had been formed in a different environment? And this is the question that we are trying to answer. So we are currently doing SEM EDS analysis, so using scan let's say form of microscope to have a better resolution of the grain and the composition on the grain. And we are looking at some elements that can give us information about the maturity of those grains. So that will give us information of are they formed locally or have they been formed somewhere else and transport on the banks. If we are now looking at the geotechnical properties, so 14 FFCPT, so freefall cone penetrometer, have been deployed on Middle Bank. Those FFCPT have been deployed, and in the superficial geology, the sand and gravel identified by Philibert in the regional superficial geology map of 2024. But laboratory testing have been done on some samples that includes grain size, Atterberg limits, consolidation test, and triaxial with bender elements, and some quick results. That's all those results will be in the report. It's not like really my expertise, but what is interesting, like one thing that can be interesting is that the Atterberg testing that have been done on the clay, silt and clay sample, it's on the bottom right panel, like graph. Let's see that you have one sample that is in the that seems to show that there is a potential elastic or organic, like elastic silt or organic soil behavior. And it's interesting because we know that organic sediment are problematic in terms for offshore wind, in terms of compressibility, in terms of gas expulsion, and also cooking cables, like heat transfer from the cables to the sediment, kind of. And so it's really preliminary, but in last year we have been able to collect a core, like it's the black sediment core that you can see on the picture in the middle. It seems to show like characteristic, or at least visual characteristic of maybe soil, and it's not really surprising because you have to realize that after the last glacial maximum, like during the marine transgression, Middle Bank was potentially exposed to was potentially exposed, and so it's not surprising that some of part of Middle Bank could be organic soil, or even like let's say clay, indirect clay, that are both really challenging for offshore wind installation. So the last initiative, we are now looking to bedrock. So the goal for this bedrock activity, like it's to see the basal conformity, the bedrock distribution, of course, and doing some subcrop map. There is a dredge and a grab sample station at the north. Like all this work are based on mostly on this dredge and grab sample in the north eastern part of Middle Bank. These results are also fed by multi-beam bathymetry, shallow industry seismic data, shallow and industry seismic data. Also nearby wells, like there is a lot of wells that have been done on Sable Bank that can may be useful for understand the geology of Middle Bank, and especially that there is you can see one well, the Dover A43, that is located on the map on the south eastern part of Middle Bank. If we are looking to bedrock results, so this is a sample from a cruise collected in 1967 that have been analyzed by my colleagues. So on the seismic data, you can see that the seismic data, like from 1984, it's almost crossing those dredge and with the rocks. So you can locate kind of the seismic data, the different type of rocks that have been collected on the bank. And so the description, so it's mostly sandstone and mudstone, and there is rare marine limestone too. And this is the result from a grab sample that I've been taking last summer. And you can, like the first interpretation that it's allowed to say that it is similar sandstone and muddy sandstone that were collected in 1967. So those have been interpreted as fluvial estuarine or shore face and inner shelf deposits. So based on all this information, the lithology of those, like showing that those rocks are consistent with the Logan Canyon formation. And if we are looking at the well, the Dover A43, so there is, sorry, like to be honest with you, I don't have access to my notes on my presentation, so like this is a lot of part of stuff done by my colleagues. So especially for bedrock, I don't have all the information, but I'm sure with Lynn in 2 days we'll have more information about the bedrocks, even if it's for Sydney Bight. So I prefer not to say something wrong, but if we are looking at subcrop mapping, so the subcrop mapping is based on the multi-channel seismic reflection and well data, like combination of both. And so what is, if you have to keep one thing is that, so the lower Cretaceous to lower Eocene bedrocks units lie below quaternary sediments, and that's confirmed that Logan Canyon Formation, it's the bedrock below the northern half of Middle Bank, and then you have like on the like the center part of Middle Bank, like the Wyandotte and Dawson Canyon forms band, which is a different type of rocks. So you have more calcareous and less completed bedrock. So that's it for this presentation. I would like to thanks all the contributors. So for each group, and also acknowledge like this is not solely a GSC work. We have a lot of collaborators in universities, and we have received a lot of help from especially the crews, the captain, the crew, and the scientific staff from the crews from NOC, and also from Leeway and Reformal, whose we have been navigated with the last 3 years. Sorry, and we also have we like to thanks the Marine Engineering and Technical Support Group at GSCA, the Geoinformatics Group of GSCA too, and also my colleague at the laboratory and collection staff of GSCA. Thank you, everybody.